we have the pleasure to hear Meixia. We talk about signal analysis via stochastic geometry of spectrogram levels.
Okay. Thank you for the introduction. And first of all, I would like to thank the committee for organizing this wonderful workshop, and thanks for the invitation. And I'm quite new in this area, and it's very lucky for me to learn from so many excellent researchers from different communities this time. And thank all the speakers for giving so many wonderful talks. And it is my great pleasure to share some of my recent work here with you. I'm going to talk about signal analysis via the stochastic geometry of spectrogram level sets. And it is a joint work with Professor Subrogosh and Mr. Dongfang Sun from NUS. This is the outline of my talk. First, I will talk about the motivations and the big picture of our work. Then we give some technical discussions on the spectrograms and white noise. After that, we talk about our main result, that is signal analysis via spectrogram level sets. Finally, we'll give some empirical investigations and conclude our talk. So first, spectrograms are fundamental tools in time frequency analysis. And informally speaking, the spectrogram of a signal associating with each point in the time frequency plane is a localized measure of the energy of the signal at that time and that frequency. And spectrograms analysis has been demonstrated to be highly effective in many applications, and a particularly significant domain of application is in the field of acoustics. For instance, AM/FM type signals with a small number of components admit spectrogram representations that are sparse, in the sense that the locations with high spectral energy are few and far between on the time frequency plane. And this allows us to give a cogent examination in terms of the structure of the original signal. So here we give some illustrations of how the spectrogram looks like. The left picture shows the spectrogram of white noise, and the right picture shows the spectrogram of one fundamental mode corroborated by the white noise. We can see that there is a peak in the right-hand side. So the different structure of these two kinds of pictures enables us to perform signal detection by using the spectrogram of signals. So classically, considerable attention has been focused on the maximum of the spectrogram. And it is related to the understanding that this will capture greater energy of the spectrogram, therefore greater information of the signal. So techniques such as synchrosqueezing, reassignment, and ridge extraction have gained prominence in the context of identifying and processing the maximum of the spectrogram. And recently, zeros of spectrogram have gained traction as effective analytical tools. And this line of investigations originates from seminal work of Flandre in 2015. And in essence, the central idea of this vein of work focus from the empirical observation of Flandre that the zeros of the Gabor spectrogram of white noise has a spatial distribution that is highly uniform on the time frequency plane. On the other hand, if we have a non-zero signal, then the existence of the non-zero signal will create distortions in the highly uniform spatial distribution. And this will enable us to perform some signal detection based on this kind of observation. And this observation has been utilized for devising empirical approach for signal analysis. We are studying the spectrogram zero set, say for example in the work of Professor Bartnick and his co-authors in 2020. And the STFT of white noise is connected to the Gaussian analytic functions, or for short GAFs. The hyperuniformity of the GAF zeros provide a cogent explanation for the empirical observation that these zeros have a highly homogeneous spatial distribution. But there are some difficulties in using spectrogram zeros to understand signals. First, the lack of integrable structure in GAF zeros will make it difficult to provide theoretical analysis. And second, the real coefficients interfere with statistical symmetric properties of GAF zeros. And lastly, the zeros can be unstable with noise and numerical errors, and this will lead to robustness issues in the numerical methods. And say, for example, suppose our observation window looks like this one, and we will observe some zeros. For example, look in this form, and it is highly uniform. And if we have some numerical instability, then the zeros may move to other place a little bit. And it may change some structure of, or it may make some difference of the whole observation we make. But if we consider the kind of the level sets of the spectrogram, then the level sets will be a connected subset of the space. So for example, our level sets look like this one. So if we have some instability, numerical instability, then most likely we'll have some oscillations near the boundary, kind of this. But the whole structure of the picture will remain the similar. Here we define the upper level set. For example, here we have X is a spectrogram. And we define the upper level set as at level theta, defined as lambda theta equal to the point UV belongs to R2 in such that the spectrogram at UV is greater than theta. That is the upper level set. Then we can see that if we take theta equal to 0 in this definition, for example, if we take theta equal to 0, then if we consider the complement of theta, if we take the complement of lambda 0, it will just be the 0 set of spectrograms. So the level set is actually a generalization of the original 0 set. So, but we can see that the level sets are more robust to noise and some numerical perturbations. And we can have some richer mathematical theory around the level sets.
So sorry, what do you mean more robust to noise than zeros? What robustness of zeros do you lack?
I mean that if we have some numerical issues or numerical instability, the zeros may move to a little bit in the space when we observe. But if we observe the level set, so if we have some numerical instability, then, for example, it is the true level set we want. But if we have some instability, we may observe kind of this one. But the whole structure may look very similar. So it is more stable or more robust.
But what could happen for the zeros? I mean, it would also, if you change your signal just a tiny bit, the zeros wouldn't move too much, right?
Yes, but the structure of this one, we can detect some of the structure of the level set. And
so the zeros, like, I mean, this structure is a bit loose, right? This structure of the zeros is also preserved.
Depends on how you mean the structure.
Totally move, right? The zeros can totally, I mean, a point is either, they are isolated points. So they can, it's either here or not here, so
Yes.
you can move somewhere else.
Yes.
So, you cannot always understand the errors in terms of the additive Gaussian noise, right? So there can be some error in transmitting or recording the zeros, for example. So if you have some small errors like that, let's say the boundary of the level set is a big set, and if you change it here and there a little bit, that's a much smaller problem. Whereas the zeros being isolated points, they can, some of them can totally move and create a whole file.
Okay. And I have the feeling that still, like, if you change f only a little bit, then the zeros wouldn't move too much.
But you are not changing it. Maybe you change the zeros because of some other kind of error in transmitting or recording.
Okay.
Maybe you erase or delete zeros.
All right. So I'm not numerically finding the zeros from a spectrogram, but someone is communicating the zeros to me and is forgetting a zero.
Yes.
All right. But for sure, there's more information in the level sets because you can basically reconstruct the spectrogram
Yes.
with the level sets and the zeros. You need a couple of coefficients more.
Yeah.
Okay, fair enough.
Thank you for the question. And here we give some pictures to show the level sets, what the level sets will look like. For example, the first picture shows the surface plot of a noisy fundamental mode. And the second one, I'm not sure whether it is clear enough. It shows the zero sets of the noisy signal. And then we increase the level sets of increase the level of the lower level sets by the following three figures. We can see that as the level theta increase, then our level sets will be larger and larger. But a similar thing here is that we have a hole and in the shape of a ring. So if we can detect this spatial structure, then we can detect that, oh, here it is a fundamental mode here. And for comparison, we plot the level set of the pure noise, and we can see that as the level theta increase, there will not be the same thing happened with when we have a fundamental mode. So based on this main difference, we may find something or find a way to detect the signal based on the level set. And here is a big picture of our work. We undertake a comparative investigations of the level sets of the Gabor spectrogram of Gaussian white noise and those of a signal calculated by the Gaussian white noise. And use this analysis as a cornerstone, we will establish theoretical foundations of a spectrogram level sets-based approach to signal analysis. To be precise, we frame our work in a nature hypothesis testing problem to decide between the pure white noise and the presence of a fundamental mode. And then we provide an efficient test of hypothesis for this kind of problem and provide theoretical guarantees for its effectiveness via the non-asymptotic bound on the power of test. And based on all this stochastic geometry, we propose an estimation procedure for a fundamental mode if we know that it is present, and then provide error bound for the accuracy of such estimation. Then since the upper level set will not contain zeros, so our result also have some theoretical implications for spectrogram zero-based approach by rigorously demonstrating that the presence of a non-trivial signal creates zero-free regions, as we see in the previous picture, and for the spectrogram on the time frequency plane. And motivated by our theoretical analysis, we will propose an algorithm for signal analysis that is intrinsic to the spectrogram data. Here, intrinsic means that we do not need some prior knowledge of regarding the signal strength or others. And this procedure is able to effectively perform signal detection and estimation for linear combination of fundamental modes as soon as they are well separated. Yeah. Then we'll come to some technical discussion of spectrogram and white noise. I think most of you are familiar with this part, so we'll go through quickly. So first, for time Fourier transforms, or for short STFT, are fundamental objects in time frequency analysis. So by introducing a window function in the traditional Fourier transform, STFT will lead to a two-dimensional representation of a signal on the time frequency plane. And for a given signal f and the window function phi, the STFT is defined as the inner product between f and shifted phi. And here the shifted means in the sense of time and frequency. Here we give the definition of the STFT, and this has been talked in the previous talk, so we just skip it. And the squared modulus of STFT is the spectrogram of the signal. And STFT with a Gaussian window we call as the Gabor transform. And we introduce the Bargmann transform of function f in L2R. And here BF should be a function from C to, on C, on the plane C. So BF should be computed by this integration. And based on the Bargmann transform, we could write down the Gabor transform of f in this beautiful form. That is, Vfg will equal to some exponential term times Bf. That is a Bargmann transform of z bar. Here z is a complex value defined by u plus iv. Okay. So before going into details, we first get some intuitive explanation. Here, suppose we consider the generative model given as observation equal to some signal strength times fundamental mode, then plus some white noise. And in our analysis, we will prove that the white noise, the Gabor spectrogram of white noise will be approximately controlled. And the fundamental mode will have some peaked structure. For example, we see in this figure, the peak will come from the fundamental mode, and other part may come from the white noise. But we can see that it is almostly controlled in some sense. And in our work, we focus our attention on the most fundamental setting for a signal, that is Hermite functions, and which form an orthonormal basis for L2 and is central to Gabor analysis. And here we denote HK be the Hermite functions. And we know that the Bargmann transform of HK is in a beautiful form like this one. Then based on this, we could write down the Gabor transform of HK. Then by using this formula, we could write down the maximum magnitude of the Gabor transform of HK given in this form. And the maximum value is obtained when u square plus v square equal to pi, k over pi. And so the maximum value is obtained on a circle, kind of this. And we can identify how the magnitude will decay around the peak. And the formula is like this one. Then after that, we need the Gaussian white noise. So before introducing Gaussian white noise, we need the definition of Schwarz space and temporal distribution. And based on, I think you are familiar with this part, so we go quickly through it. So based on this definition, we could define the white noise measure mu1 in a classical way. So let Kc be a random variable with distribution mu1. So Kc here is just the Gaussian white noise. Then Kc could be written in this form. At the beginning of the previous talk, we have seen Kc equal to the summation of k equal to 0 to infinity, and the real coefficients is the Kc inner product with Hk. And we know that the coefficients here are real and it is RID Gaussian. And then for let uv equal to uv belongs to R and write down z equal to u plus iv, which is a complex number, we could write down the Gabor transform of Kc in this form. And we can see that this, we write down Vg Kc in as a limit, a function limit in L2 mu1. And the right hand side, we can see that it is a standard planar Gaussian analytic function, the blue part. And we know that the Vg C is which is a Gabor transform of Gaussian white noise. It is a Gaussian random field on R2. And it will induce a metric geometry on R2 that fundamentally determines the statistical behavior of the Gabor spectrogram. So specifically, we can write down the metric D in this form. Here we compute D square between U1 V1 and U2 V2 by the expectation of the square of difference of two Gabor transform and then take square root. We could write down the explicit formula in the second line, and we can see that the cosine term will be oscillatory, and it is related to the oscillatory behavior of the correlations of Gaussian field, and it is a main difficult when we understand this kind of metric. And it is known to create complications in the stochastic geometry of level sets. That is the red part, the cosine part. And for example, this has appeared in the phase transition phenomenon for level set percolation in Gaussian free fields. Okay, so in order to identify the noisy fundamental modes, we need the boundedness of the Gabor spectrogram of white noise, as we see in the previous picture. Here I add the quotation. Here is that it is kind of approximately boundedness, not the true bound. Okay, so it is a main theorem of our work. So we prove that for L greater or equal than pi, the probability, and for a given parameter tau greater than 0, the probability of the supremum of the Gabor spectrogram, the magnitude of Gabor spectrogram of the white noise is bounded by some constant time square root of log L is with high probability. And here we use BL be the observation window, and it is a L infinity ball in R2 and with size L. So we can see from this picture that we prove that the Gabor's transform is bounded by some constant, kind of constant, C times square root of log L, and with high probability. And now we can see that the term square root of log L will not be so large. It is pretty small in practice. For example, if we take L to be a large number, for example, L equal to 1 billion, then square root of log L will only equal to 3. So it is almostly bounded in this sense. So just a few words about the proof. So we can prove by the Borel-Tis inequality and Dudley's entropy integral, we can prove that the supremum of the magnitude of spectrogram is bounded by some constant times the integral of the square root of log. The inside part is the metric entropy function n, and plus some parameter rho. And here n is the smallest number of balls in this form that cover BL. And this ball means that the center is T and the radius is epsilon under the metric D. D is just we defined before. So in order to control this integral, we divided it into 3 parts. And so first, we use different arguments for different scales. For the first part, from 0 to L to power minus 2, we notice that the maximum of this one, smaller than order 1 over square root of L, will imply the D, the metric D between U1, V1, U2, V2 smaller than 0. And by this observation, we know that the number of balls will be controlled by the number of cubics. Of course, this ball and cubic are under different metric. So based on this, we could control the first one. And for the second one, we just use the monotonicity of the metric entropy function. And one trick here is that we change the infinity to 2 times square root of pi. The reason here is that we can prove that the metric D is upper bounded by 2 times square root of pi. So we can just cut down the interval to be 2 times square root of pi. Then based on these two terms, we can prove that, okay, the integral is bounded by some constant c times the square root of log L. And that is the main idea of our proof. And based on this theorem, we could focus on our spectrogram level sets of a noisy fundamental mode. That's what we want. So we first define the spectrogram level set of a signal Y restricted to BL. BL is what we defined before, the L infinity ball in L2. And then given the threshold gamma, we define the upper level set as lambda gamma equal to UV, the point UV in the observation window BL, such that the magnitude of phi GY, the Gabor spectrogram of Y, greater or equal than gamma. That's the spectrogram level set we focus on. And we can give this theorem to demonstrate that as long as our signal strength lambda be large enough in the order of square root of log L, then we could prove that for L greater than maximum of square root of k over pi and pi, we have that the red part says that we can prove specified the level set will be non-empty with high probability here. So now, again, we emphasize that the square root of log L will not be so large in practice. It is a pretty small number in practice. Then based on this, we have proved that for some kind of large or significant fundamental mode, the signal, and we can conduct signal detection via the spectrogram level sets based on this theorem. So after that, we could go to our main result, that is a signal analysis via spectrogram level sets. So first, we get our generative model. We assume that the observation Y is generated as Y equal to lambda times HK plus Kc. Here, HK is what we call Hermite function before, and now we assume that K here is chosen between 1 to K0, where K0 is a given number, given integer. And white noise Kc is a random variable with distribution mu1, what we defined before. And lambda here is the signal strength. And we assume our observation window like this one. The level set lambda theta at any level theta may be observed. That's our observation window. And so now we have some natural questions. The first one is that based on the observation, we will ask whether a fundamental mode exists. That's the first question. Then, if it exists, then which is the fundamental mode? That means what is the K in this model? Okay, HK here, what is K here? And the next question is that if we know what is HK now, then the next question is what is the signal strength? That is, what is lambda here? So we will answer these three questions one by one. So first, we will detect whether there exists a signal or not. So we frame our signal detection problem in terms of a simple various composite hypothesis testing problem. So to be precise, we test our non and alternative hypothesis like this form. First, H0 means a non-hypothesis. That is the observation Y just equal to the white noise Kc. That means there is no signal, only noise in our model. And H1 is the observation y equal to lambda times hk plus kc, with lambda not equal to 0, which means we actually have a signal in our observation. That is our H0 and H1. And then a test psi theta is a measurable function of the observed level set, lambda theta. And we'll map the lambda theta to the two-element set, 0 or 1. And with the understanding that the value 0 will correspond to we will accept H0, and the value 1 will pretend to reject the non-hypothesis and accept the alternative hypothesis, H1. So then we define the P0 be the distribution of lambda theta under H0 and the PM of distribution of lambda theta under H1, here with k equal to m. Then we say that we detect the signal at strength lambda. If for any delta greater than 0, there exists a test psi at theta delta such that the P0 at psi theta delta equal to 1 and takes the maximum of 1 k from 1 to k0 pk psi theta delta equal to 0, and all this part smaller or equal than delta. And then we say that we detect the signal. Note that the first part corresponds to the probability of type 1 error. Type 1 error means that we reject the non-hypothesis, but it is true. And the second part means the type 2 error in this model. Type 2 error means that we fail to reject the non-hypothesis, but it is actually false. So we control this type 1 and type 2 error in this problem. And we want an algorithm for signal detection when the probability of these two types error are less than delta. That's what we want. And then we just consider the tests of the form like psi theta equal to the indicator function of the lambda theta is non-empty. So it will map lambda theta to a 0, 1 set. Then we could provide the theoretical guarantees for the proposed test of hypothesis, which means suppose we have an error threshold delta greater than 0, and it is given, and we consider the test psi at theta delta by citing theta delta in this form, which is in the order of square root of log L plus the square root of log 1 over delta. Then we prove that for L large enough, greater than right-hand side, we can say that the psi theta delta will perform signal detection with error threshold delta if the signal strength is greater than the right-hand side. And mk0 here is a constant of k0 defined in this way. So that means that as long as the signal strength is large enough, our proposed test can give us the signal detection. Okay, so now we know how to detect whether there is a signal or not. So now suppose we know that there is a fundamental mode. So we know there is a here. So what is it? That's the question. So we need an estimation procedure to estimate the k in our model. So we demonstrated that the signal estimation is possible with high probability as the observation size L goes to infinity. So before going to our result, we define some statistics. First, theta hat be the maximum of theta such that lambda theta is not empty, and k hat be defined in the right-hand side. So we will here, this notation means that the nearest integer of x belongs to R. And k hat is actually what we estimate k. That's our estimation of k. And based on theta hat and k hat, we could define the lambda hat. Lambda hat is that the theta hat over some product of this square root part. So here, lambda hat, we will prove later that it is actually the estimation of the signal strength lambda in our model. So the k hat, lambda hat, that's what we want in our estimation. Then we give some proof for a given parameter tau greater than 0 and for large enough L. And for signal strength lambda greater or equal than T mod tau, that is a constant in the right hand side associated with K0 and square root of log L. Then for this large enough signal strength, we can prove that the infimum of this part of this probability will greater or equal than a number very close to 1. That means we could detect or we could estimate the k with high probability. Now, why we take the infimum of the probability here is that in our alternative hypothesis, we have multiple cases. So the left-hand side means the worst we can do. So we take infimum here. Then now we estimate the mode, the k. And we can see that the theorem provides an error bound for the accuracy of the mode obtained by our estimation and in terms of the quantity of data available. Then after that, we need to provide an estimation procedure to the signal strength as we talked before. So here is the main theorem for again for large enough L and signal strength large enough. Now we change another constant T strength here. Will defined as the order of log L. Previously is the square root of log L, but both of them are very small number in practice. So we can prove that the infimum of the probability that we estimate lambda correct with the error delta will be very high, will be close to 1. That means with high probability, we can estimate lambda hat with a very small error delta here. So based on all of this theoretical analysis or mathematically rigorous understanding of the spectrogram level sets, we could provide an algorithm for signal detection and estimation. So the first step, we compute the Gabor spectrogram VGY for a given signal Y and respect to the Gaussian window function G. And given L large enough, we can compute ML. ML is that the maximum value in the observation window. So maximum value of the magnitude of spectrogram inside the observation window. Then we compute the level set. We just take lambda at the level 0.2 times ML, just defined previously. So now the question is that why we choose 0.2? Intuitively, we want a number that will intrinsic to the input data. So this will make our algorithm more generalized to more cases. And first, this number will not be so close to 1 and so close to 0. Since previously we have drawn the spectrogram of the noisy fundamental mode, it will have a peak and other parts will have some small peaks. And so we want something kind of in the middle, around the middle, to help us detect the shape of ring in our previous picture. So, and empirical experiments show that the 0.2 is actually a very good choice for most of the cases. So here we just use a constant 0.2 times the maximum of the spectrogram. And then we will detect whether there exists a ring in this kind of level set. If we have a ring, then we say that, okay, there exists a fundamental mode. Then after that, suppose we know that there exists a fundamental mode, then we will say, for example, now we have the spectrogram like this one, and we detect that after step 3, we know that we have a structure like this one. Then we say that we have a fundamental mode. The next question, what is K? So we just, since when we compute the spectrogram, we get some screen in the space. And we show from the origin point, we use different K or slopes to draw some lines like this one, and to detect or to intersect with our level set to see this kind of points, and to detect the radius of the large cycle and the radius of the small cycle, and to take kind of average of these two to determine what is a K. Since when we estimate when we compute the maximum magnitude of spectrogram of Hermite function, we know that the maximum value will obtain on a cycle. So we assume, or kind of this maximum will be around this one. Then we estimate the K based on this idea. Then here are some words after regarding the algorithm. So a key feature of the algorithm is that its operation is intrinsic to the spectrogram data. That is, we choose the 0.2 in all cases. And in particular, it does not depend on prior knowledge of additional information. That is what I said before. When we making the choice of threshold for the level sets, it will not change for different cases. And note that an important thing here is that we only care about the level set itself, not the values of spectrogram in this area. So back to our algorithm, our level set will be a 0-1 matrix. We just focus on this 0-1 matrix, not the values. We don't care about what is a specific spectrogram on the set. So just a side note, since up to now we only care about the one fundamental mode. And this procedure actually can be extended to the linear combination of fundamental modes as long as the signals being combined are reasonably well separated, which means when we draw the spectrogram or the level set spectrogram, the rings are well separated. Then we can estimate this kind of signal by our algorithm. Okay, so we come to the empirical investigations. So before we talk about the numerical results, we first define the modified accuracy. So in order to measure the performance of our algorithm for learning linear combination of fundamental modes, for example, the summation of I equal to m is a given number of modes, then be lambda I times hki. And lambda I here is each signal strength, and hki is different Hermite functions. And it will have some white noise. So, and we suppose ki is bounded, that is, it will not be too large. We have a k0 upper bounded. Then we provide a reasonable matrix. That is to say, we define the MACC of the estimation. Here, estimation, k hat and m hat is what we get from our algorithm. And the simple one is that, okay, if m hat not equal to m, for example, we actually have 3 fundamental modes, but only estimate 2, then totally wrong. The accuracy will equal to 0. And the last part, if the number of modes is correct, but the difference of ki hat and ki is very large, then we just set the accuracy as 0, which means we totally wrong. And the inside, the middle part is a little bit complicated. The reason here is that it is known the Hermite function or fundamental modes are very similar as functions if k, for k and k plus 1, if k is very large. They are very close. So it is difficult to identify, for example, H20 and H21, for instance. But this will not work for the small k, such as k equal to 1 or 2. They are quite different. So we just take this into account and define this kind of accuracy. Then by definition, we can see that if the MACC equal to 1 means we have perfect estimation, that is totally right. And MACC equal to 0 means the worst, means we get the wrong estimation. So now we come to the first part of the numerical experiments. We consider y equal to lambda times hk plus sigma times kc. Here the integer k is uniformly generated, and the signal strength lambda is uniformly generated in between 1 and 2. And we take the noise strength sigma equal to the order of 1 over square root of log L. And we fix the observation window size L equal to 8. And for each case, as we said in our algorithm, we define the spectrogram level set like this one. Then we give some picture to show what we will get. So for example, we take K in our case. Then the left-hand side shows the Gabor spectrogram, just the Euro case. And the right-hand side shows our spectrogram level sets. We can see that it exists a ring, not so smooth, but it is a ring. So the non-smooth part comes from the noise or some numerical issues. And then this picture shows the result of K equal to 100, another case, still a ring, but a larger ring in our observation window. And we can see that this ring will enable us to detect the fundamental mode through this spatial structure. Okay, so numerical results show that the level sets as 20% of maximum, 20% just 0.2 we talked before, will lead to signal estimation of one fundamental mode with accuracy greater than 99%. And the accuracy here just in the sense of MACC I defined before. So then we come to the case of 2 or more fundamental modes, which means we test the generative model y equal to the summation of I equal to m lambda hki plus some noise, and ki here are uniformly generated. And as I say, we need the fundamental modes to be well separated for our algorithm to work. If they are too close, for example, k equal to 20 and 22, then our algorithm may not work. So here we generated ki to ensure that they are separated. And here the parameter omega is to kind of control how separated they are. And if we take a large omega, then it will be more separated. Okay, so here is a picture of 2 fundamental modes, K1 equal to 8 and K2 equal to 90, very separated. We have 2 rings in the picture, very beautiful. Then it is a tree, if we have 3 fundamental modes, and we have 3 rings here, and we can see some of them are connected, but it will not affect our result since we will draw many slopes to detect the ring. So this part, kind of the noise or others, will not affect our result. Then for better illustration, we get the table to show the empirical performance of our algorithm for learning linear combination of fundamental modes. And we run our experiments in 10,000 times with different parameter omega. And we can see that we show the result of fundamental modes equal to 2 or 3, and we set different value of omega, 1.5 and 2. And as we said before, the larger omega will give us more separated fundamental modes. So the accuracy should be higher, and the result coincides with what we expect. So, and we can see the last column is that our accuracy is always larger than 19%. Okay, so overall, our algorithm is quite effective for learning linear combination of fundamental modes, as long as these modes are reasonably well separated. Okay, so here is the conclusion. In our work, we have investigated signal analysis via an examination of stochastic geometry, properties of spectrogram level sets, and we obtained regular theorems demonstrating the effectiveness of a spectrogram level set-based approach to the detection and estimation of signals, and further propose a level set-based algorithm for signal analysis that is intrinsic to given spectrogram data. And we hope that this work will serve as a prototype and provide a roadmap for similar investigations with respect to broader class of signal, since in our work we only care about the fundamental modes taken as a Hermite function. And for example, some possible direction is that we can investigate the complex valued analytic chirps, some kind of this. Okay, here is a reference of this work, and thank you all for your attention.
Yes, maybe I missed something, but I have the feeling that there should be a coupling between the level, the 0.2, let's say, and the signal-to-noise ratio. Does it seem that you fix the signal-to-noise ratio, or have you result of your performance as a function of the signal-to-noise ratio?
Okay, so
I don't see why here in your simulation you fix the level of the noise.
no. Wait a moment. Let me turn back to the slides.
The model.
Okay.
Yes.
So okay.
Sigma.
Yeah, I fixed the sigma, but I change lambda here to, since lambda is random, so the since we.
Yeah, but the lowest SNR is fixed.
Which one is fixed?
So there is a lowest possible SNR by lambda being.
Yes, since in our result we show that we must need a strong enough signal. So
But let's say the range of variation of your lambda is quite small.
yeah, so not so large. But if it is too small, then our algorithm will not work. But if lambda is larger, then obviously we will get the result. Since the signal, if signal is very large, then we can detect the ring easily.
So regarding your theoretical results, if I didn't miss anything, most of them depended only on the maximum of the spectrogram, didn't it? So
Which?
did you in any of the theoretical results actually use the geometry of the set?
Yes, since the wait a moment. In all these experiments in the third part, mainly focus on the first theorem I mentioned, that is the one I give some proof. So the most of them start from this theorem, and they will use
Okay,
that
but this could also just be formulated for the maximum of the spectrogram.
the maximum of the white noise, a spectrogram of white noise is
Exactly.
controlled. Yeah, correct.
Yeah, so why do you actually need the level set and not just test for the location of, or the value of the absolute the global maximum, let's say,
Global maximum of
of
you.
the spectrogram?
Then that's the case that, for example, we have some noise or numerical issues, how it will look like. Since if we see this picture, here, if we look at the maximum, it will not be a ring. It may be.
No, but it will most likely be on the ring.
But if we see from this picture, some part will decay because of we have some noise. Not. If we draw the maximum of this spectrogram, it will look like kind of.
No, it will be
No,
one
no.
point. It will just be one point with probability 1 most likely, right?
You mean we only detect one maximum?
Yes. Global maximum, not local maximum, but really global maximum. That global maximum of the spectrum.
Then how you tell the difference between these two?
What we want to do, right? That's
Yeah, detecting signal. And
Yeah,
so
for example,
like
if you look at
a simplification of this thing would be you try to detect the global maximum and then you just take
Sure, but
where it is taken.
Sure, but the point is that if you do not have signal, so the null hypothesis, when there is pure
Yes.
noise,
Then it will be small.
yeah, I mean it's just a single point.
Yeah, but the value of the single point can can serve as a
Sure, but working with single points, single isolated points is exactly what we want to apply.
but do
Because that single point is very sensitive to, you know, recording and transmission errors.
Yeah, but you're gonna transmit in your case level sets?
I mean,
You transmit the whole spectrogram, right?
in our setup, we use the spectrogram as given, so we do not directly use the signal in any way.
Then
So
you
it is
could
not like we are taking the signal and calculating the spectrogram. We take the spectrogram as given and only query the level set at some input there. So that's the only thing that I do.
then you could get the maximum, right? And if you take the spectrum.
Sure, but we don't know how accurate this spectrogram that is given to us is.
So you assume that maximum will actually be more
Yes.
less robust again than the level set?
but the theoretical results fundamentally depend all only on the maximum, right?
The size of the maximum.
Exactly. Yeah.
Because you need to basically dominate the
Yeah,
point by
exactly.
the
Yes,
signal.
yes. So it doesn't really make use of the geometric properties of the level set.
I mean, not yet. In principle, it would, but
Yeah, sure, but this because your algorithm kind of uses these geometric properties, right?
yes,
But kind of the theoretical results do not,
yes.
right? Okay.
I think it's time to move to the next talk. Thanks again.
Thank you.